volumetric analysis, doing a titration. We've got an example here of a nice titration, and we're going to do the calculation for this titration here. The titration involves an antacid tablet containing magnesium hydroxide as the active ingredient. This is dissolved and added to a 50 ml volumetric flask. 25 ml aliquot of this solution is titrated against hydrochloric acid, and we get an average titer here. What we need to find out is the percentage of active ingredient in the tablet. So let's have a look at how I'm going to solve this. Because I know it's a titration, the first thing I really need to do is I need to find out an equation. What is my equation going to be? So magnesium hydroxide is the active ingredient, so that's what we're going to be looking for. So I'll write down magnesium hydroxide, MgOH2. Okay, magnesium's 2+, hydroxide's negative, so that's why you need two of these. You add that to hydrochloric acid because that's what's happening in the titration. And we form magnesium chloride and water. Okay, pretty simple acid-base reaction there. Okay, two of these, so therefore it's not balanced. I need two of these, and I also need two of these to make it balanced. Now I have a balanced equation. I'd like to have states in there as well, so why not put states in there? I'll put them in under blue. This is going to be aqueous, this is going to be aqueous, this is going to be aqueous, and this is going to be liquid. We have our balanced equation. Let's write down what we have underneath these things. I don't know how much is magnesium hydroxide. We want to find out how much magnesium hydroxide we have. We want to find out the active ingredient. We do, however, have a molarity of hydrochloric acid, and we have an amount of hydrochloric acid. So I'm going to write that down underneath our hydrochloric acid. 0.25 molar and 13.70 mil. And we don't know this. That's what we want to find out. How much is there? You can also look at this and see what's happened as well. I might just draw a little flow chart quickly because I know there's a bit of stuff happening here. What's happened if I have a tablet? That goes into 50 mils. From that, I get 25 mils out, and I react this with HCl. Alright, so that just tells me a bit more about what's going on. Quick flow chart telling you what's happening in this. I have a tablet going into 50 mils, and I'm taking 25 mils out of that, reacting with hydrochloric acid. That's going to help me later on, believe me. So, I have my equation, I have my information. From this I can get number of moles of hydrochloric acid. N equals C times V, which equals to 0.25 times 0.01370. Because, remember, mils must be converted to litres. I'll get my trusty calculator out. 0.25 times 0.0137 equals 3.425 times 10 to the power of negative 3 mole. So therefore I have my mole of hydrochloric acid. I want to find out my mole of magnesium hydroxide, so I must do a ratio. So I do number of moles of HCl divided by 2, because the coefficient is 2, equals number of moles of MgOH2 over 1. So therefore I have 3.425 times 10 to the negative 3 divided by 2 equals the number of moles of magnesium hydroxide. And let's just work that out. I quickly go answer divided by 2 equals 1.7125 times 10 to the power of negative 3 equals my number of moles of MgOH2. So, I have my number of moles of magnesium hydroxide. What am I working out? Percentage of active ingredient. So that means I need to get a mass, because I started off with a mass here as well. So, my mass, I'll do this in another colour, my mass of MgOH2 equals number of moles times molar mass. My molar mass is going to be, what is it? Magnesium is 24, plus 2 oxygens is 32, plus 2 hydrogens is 2, so 34 plus that is 56 plus 2, 58. So it's going to be this number here, 1.7125 times 10 to the power of negative 3 times 58. It's going to be my mass of this. So where's my old number? 1.7125 times 10 to the power of negative 3 equals, times 58 equals 0.099325 grams. Now, let's have a look at this. Is this how much is in my tablet? No. Want to know why? Because I've looked at this. What I've done, this is 0.099, what was it? 325 grams. This was in my 25 ml aliquot. Alright, so I'm going to write down here, in 25 ml aliquot. This is only half of what I had originally. So really, in my 50 ml, which was in my tablet, was double this. So really, my mass of MgOH2 in the tablet will be twice this amount, which will be I'll write it down here properly, 99325 times 2 equals 0.19865 grams is actually in my tablet. Is this what my question asked me? No. My question asked me for the percentage of the active ingredient in the tablet. My tablet weighed this much, so I'm going to go percentage. If I get a colour that works, percentage equals 0.19865 divided by 1.3 times 100%, and I'll get my percentage. Divided by 1.3 equals that, times 100%, 15.28%. Now, is that my final answer? Not just yet. I still need to check to make sure I've got the right number of significant figures. I'll come back down here, I'll go count my significant figures on each thing. I've got 1, 2, 3 significant figures in this one. 1, 2, 1, 2, 1, 2, 3. My smallest is 1, 2 significant figures. So I'm going to cut this down to being 15% is my answer. Once again, a recap of how I worked this question out. I started off by a little flowchart saying what's happened to my tablet to see either my dilutions or what's happened to where I'm working out the amounts in my stoichiometry. I then start to do my stoichiometry. I write an equation down, write down the information I have. From this information I can see that I get my number of moles of hydrochloric acid. I do a ratio, work out my number of moles of magnesium hydroxide. I get a mass of magnesium hydroxide. I then use that mass of magnesium hydroxide to go back into how much was in my tablet by doing either dilutions, if it happened to be, or whether I've taken an aliquot out of a larger sample. This little part here is quite important because this is a part that's going to be quite tricky for you most of the time. Your stoichiometry is going to be pretty easy because you're going to do it so much. What's going to change each time is what happens in the preparation before you do your titration. So just be wary of that. Percentage, simple, how much you have divided by the total equals percentage. There you have it. Simple titration. Done. Okay, another volumetric analysis question. This time we're doing something known as a back titration, which is, it's a real fun type of titration really, so we'll get straight into it and have a look at it anyway. Let's read through our question, let's try and work out and write down some information that we can find out. A 1.234 gram of sample of lawn fertilizer containing ammonium ions was diluted to make 250 ml solution. 20 ml of this solution was reacted with 20 ml of solution of sodium hydroxide. Once all ammonium was reacted, the excess sodium hydroxide was titrated against hydrochloric acid. The endpoint was found when that much had been added. Acid had been added. Calculate the percentage of nitrogen in the sample of fertilizer. All right, let's quickly draw a flowchart of what's happening. We have some fertilizer. This made up to 250 mil. So we have that much fertilizer going to 250 mil. From this we take 20 mil and react it with NaOH. Okay. Once we've done that, we obviously have excess sodium hydroxide. So sodium hydroxide is excess, and that's added to hydrochloric acid, and we get a endpoint of hydrochloric acid. So let's write down some quick what are called equations, and we can look at what's happening here. First equation is we have ammonium ions, NH4+. We're adding that to sodium hydroxide. So sodium hydroxide is being added to it, and it will form, well, this is going to be a base, so it's going to form sodium, it's going to form, what is it going to form? It's going to form water anyway. It's going to be a 1-to-1 ratio. Okay, so that goes there, and it's going to form ammonia, apparently, and perhaps, who knows what it's actually going to form, but that's going to happen to it. It's going to be a 1-to-1 ratio here. Second thing is sodium hydroxide, NaOH plus HCl, forming water and sodium chloride. So we have these two equations happening. Now, this is a back titration, so you have the two things happening. Okay, I'll do a little demonstration of how this is going to work. What you have is a certain number of NH4+ ions. We can't titrate these really well because it's a weak acid. So what we do is we add a whole bunch of OH negative. And then what we do is we titrate the rest of the OH negative with HCl. We know this amount, we know the whole amount here, so we can work out how much must have reacted here. Let's just do that in a question. First of all, endpoint of 9.97 mils of acid against sodium hydroxide. So what we're going to do is go number of moles of HCl equals C times V equals concentration is up here as being 0.1132 times volume 0.00997, because we have to convert it to mils, remember. 0.1132 times 0.00997 equals 1.12 times 13, if I don't round it properly, times 10 to the negative 3 moles. Okay, this is going to be the excess. Okay, remember once all ammonium reacted, the excess sodium hydroxide was titrated against hydrochloric acid. So this is sodium hydroxide in excess. What we can do is a ratio, 1-to-1 ratio of hydrochloric acid to sodium hydroxide. That means that is equal to the number of moles of NaOH excess. All right, write it down like that. We can also work out how much was initially added completely to our, all of it was added here. Okay, so number of moles of NaOH total, how much was completely added? We have a molarity and a volume. So we have times C times V equals 0.1022, can't read that, times 0.02 because we added 20 mils of it. 2.044 times 10 to the negative 3 moles. So what we have is the total amount added and how much was left over. So what we can work out is the number of moles of NaOH that reacted. It's going to be equal to the total, take away the excess, which is going to be equal to 2.044 times 10 to the negative 3, take away 1.1213, times 10 to the negative 3. And that will be equal to, take away, brackets, 1.13 times 10 to the power of negative 3 divided by, bracket, means we have the amount that reacted was 9.14 times 10 to the power of negative 4 mole. So this is how much reacted in our first equation. Okay, so if you look at this, this is what we found out first. I'll put it in here. This is the first one we found out, which told us how much reacted here. The second was our green, here, the total. From this, we can work out how much reacted with our ammonia. So our number of moles of this is what reacted. So I'll put reacted here. We have a 1-to-1 ratio between the sodium hydroxide and the ammonia. So we have, this will be equal to the number of moles of ammonia. Okay? So therefore, from this, we can say we want to know the percentage of nitrogen in the sample of fertilizer. Okay? This is also equal to the number of moles of nitrogen because we have one nitrogen in every ammonia, which means we have this much nitrogen. We can get a mass of nitrogen, which will be equal to number of moles times molar mass, 9.14 times 10 to the power of negative 4 times the molar mass of nitrogen, 14. Our mass of nitrogen will be times 14, 0.012796 grams of nitrogen. Percentage of nitrogen is equal to 0.012796 divided by 1.234, which is our initial amount of fertilizer, divided by 1.234 times 100%, means we have 1.04% nitrogen in our fertilizer. Now, this is a pretty complicated question. Back titrations generally are, but let's just go through it again and I'll try and explain it in simple terms as much as I can. Actually, I've forgotten something. Anyway, I'll go to that in a second. What I've worked out is I've written down two equations here. 1, 2. First equation, first reaction. Second equation with the excess. So I've also written down a quick thing here for a back titration. What we have, adding excess OH and then adding the hydrochloric acid. I've written down the hydrochloric acid reacting with the excess sodium hydroxide, and I've got this as being what reacted. I first of all find out the number of moles of my excess sodium hydroxide by working out stoic with hydrochloric acid. I find this out. I then work out my total number of sodium hydroxide that was added originally, which is this. I then work out how much sodium hydroxide is reacted with, so total, take away the excess. So I work out this amount. From this amount, I work out how much ammonia was there in my aliquot, which is where I stuffed up. Okay, I need to go back and look at this. This is the mass that was in my 20 ml aliquot. Okay, looking up here, remember, 20 mils was taken from 250 mils. So really, what I should have done is multiplied this by 12.5 to get from 20 mils will be equal to how much is in 250 mils. So let's just go back and divide that by, and I get my grams here. I should multiply this by 12.5, and that is my mass in my fertilizer. Because I forgot my first step here of looking at my dilutions. Now, I've got my mass there, so therefore I should change this to being my percentage. 0.15 grams divided by 1.234 times 100 equals times 100, 12.96%. And that looks a bit better in fertilizer. All right, that's the question done. I apologise for my stuffing up of this question, but hopefully that has given you an idea about why it's important to draw your little flow chart of what's happening in the question. Any questions, please give me a yell. Okay, more volumetric analysis. This time it's a redox titration, and it's working out the amount of ethanol in a certain liqueur. It gives a bit of a detail here about what's happening. So in the volumetric analysis of ethanol, ethanol is converted to ethanoic acid and dichromate ions to chromium 3. So a 10 ml sample of liqueur is diluted to 200 mils with distilled water. 20 mils of this diluted sample is titrated against 0.100 molar potassium dichromate and reaches an endpoint of this. First question is write two half equations and a full equation for the volumetric analysis of ethanol. Alright, this is going to be fun. This is redox. And then we want to calculate the percentage by volume of ethanol in the liqueur. Let's start off with our redox thing. So our first one is looking at our half equations. Excuse me. Ethanol, C2H5OH, is converted to ethanoic acid, C2 or CH3COOH. We need to balance this half equation by adding certain things. Alright, first of all, we balance off everything that is not hydrogen and oxygen, and they already are 2 carbons here, 2 carbons here. Done. Alright, this is going to be liquid, and this is going to be liquid as well. Is it? Might be aqueous. These are going to be aqueous actually, because they're solutions. Balance oxygen with water. That's what you need to do next. So we've got 1 oxygen here, 2 oxygens there. So I need to add a water to this side. And therefore we have it balanced in the oxygens. We next need to balance out our hydrogens. So 5, 6, 7, 8 on this side and just 4 here. So I need to balance it off with 4 hydrogens on this side by my count. Yep. So therefore we have our hydrogens balanced, and now we need to balance our charge by adding 4 electrons to this side because no charge on this side and 4 positives on this side, which means 4 electrons need to go on this side. Waters are always liquid, hydrogen ions are aqueous, and our electrons have no charge whatsoever. So there's our first half equation. Our second half equation is the dichromate ion here being converted to chromium 3. So therefore, I'll go back to writing out what we have. Dichromate is Cr2O72 negative, and the chromium ion is 3 plus. These will also be aqueous because they're in solution. How do we balance it off this? We start off with balancing everything that is not oxygen and hydrogen. So 2 chromiums here, only 1 there, so we need to put a 2 here, first of all. Next up is balancing our oxygen with water. 7 oxygens here, which means 7 waters on this side. And then we need to balance off our hydrogens. No hydrogens here. 7 times 2 is 14 hydrogens on this side, so therefore we need 14 H plus aqueous on this side. And now we need to balance our charge. Overall we have 2 times 3 is 6 positive on this side, 14 positive on this side. So how do I get down to 6 positive from 14 positive? I need to add 8 electrons to this side. And therefore I have my 2 half equations. Need to make a full chemical equation, so I need to add these 2 half equations together. How am I going to do that? I need to balance off my electrons. I've got 8 on this half equation, 4 on this half equation, so this one must be multiplied by 2. So therefore, and then I add the 2 together. So I'll end up with, I'll do it in black. I'll start over this side. 2 ethanol, CH5OH, plus 2 waters, H2O, plus a dichromate, plus 14H plus, and that's everything on this side. Everything at the top here is multiplied by 2, remember. And that will form, what's on this side? 2 ethanoate, CH3COOH, plus 2 times 4 is 8 H plus 2 chromiums, plus 7 waters. And now I look and I cancel out the stuff that is on both sides. 2 waters here, 7 waters here. Cross this off, and this one goes down to 5. 14H plus on this side, just 8 on this side. Cross this off, this goes down to 6. And then I can write out the whole thing again without these things. So it's going to be 2C2H5OH plus Cr2O72 negative goes to 2CH3COOH plus 2Cr23 neg plus 5H2O. Full equation: aqueous, 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 liquid. And therefore we have our full chemical equation from our 2 half equations. That's the first part of it, writing our half equations. While I've got you here, let's just look at which one's going to be oxidation, which one's reduction. Believe it or not, I've lost an electron, that's oxidation, so electrons are on the right. Electrons are on the right here in our first one, so this is our oxidation half equation, and this must be our reduction half equation. So therefore we have our more information for you anyway. What we need to do is calculate the percentage by volume of ethanol now. So I'll quickly get onto this. Okay, calculating the percentage by volume of ethanol in this liqueur. And this is where we're going to use this information now. 10 mils of liqueur diluted to 200 mils with distilled water, 20 mils taken, titrated against that. So let's quickly do my flowchart. I'll have 10 mils of liqueur. This is going into a bigger thing to make 100 mils of diluted liqueur. What's happening? 20 mils is coming out and added to K2Cr2O7. Alright, and therefore that's where our titration is. Let's have a look at what's going on. We have our reaction already, we have our equation here. Okay, I'm not going to do too much more from this. I'll just write down the information that we have. We've got 0.1 molar of potassium dichromate, and we have 24.61 mils of it as well. So from this information, we get our number of moles of potassium dichromate. Number of moles of dichromate, equals C times V equals 0.1 times 0.0246, because we need to convert our mils to litres. Equals, calculator handy, 0.1 times 0.02461 equals 2.461 times 10th power of negative 3 is our moles of potassium dichromate. Okay, we have a reaction between dichromate and ethanol. Want to know what? We can get ratio, we can work out how much we have of ethanol. So let's go for number of moles of our ethanol, our dichromate, over 1 equals number of moles of C2H5OH over 2, because that's what it says there. Okay, you can see our ratio 2 to 1, so therefore we have our ratio here. That means 2 times number of moles of dichromate equals our number of moles of ethanol, which will be equal to, times that by 2, 4.922 times 10 to the power of negative 3 mole. Okay, so we have our moles of ethanol in our 20 mils here. All right. Percentage by volume of ethanol. All right. Percentage by volume of ethanol, we need to go into grams, all right, first, and then we can go from grams into mils if we want to. But we'll go for mass of ethanol. I'm just going to call it F now because it makes it a bit easier for me. Equals number of moles times molar mass. My molar mass of ethanol is 2 times 12 plus 6 plus 16. So 24 plus 6 is 30 plus 16 equals 46. So it's 4.1922 times 10 to the power of negative 3 times our molar mass of 46 equals 0.2264 grams in 20 mil. Diluted. Remember, this is all in this 20 mils of diluted. Okay, interesting fact, the density of ethanol is approximately 0.7 grams per mil. Alright, so what we can do is from this amount of grams, we can get how many mils we have. Alright, this will normally be given to you, I think it's about 0.7. I'm happy with 0.7. So from this, we can go from grams into mil, divide this by the density, you'll get, divide by 0.7, equals 0.323 mils in 20 mils of diluted solution. Alright. You've diluted it by a factor of 10. 10 mils to 100 mils. Alright. So therefore, what we can look at is if this was to go to the undiluted, you multiply it by 10. Just by looking at it, just seeing like, I can understand that. I can understand this dilution factor. Dilution factor is by a factor of 10. So when it's undiluted, it'll be 10 times concentrated. So therefore, you'd have 3.23 mils in 20 mils for your undiluted solution. From this, you can work out a percentage. You'll get 3.23 divided by 20 times 100 will give you your percentage by volume times 10 divided by 20 times 100 equals 16.17% is the percentage of alcohol in your liqueur. Now, let's just go through how I work this out again. First things first, we needed the equation. We got the equation by looking at what information was given to us in the question, and therefore our equation is this. We wrote down what we knew. We knew potassium dichromate and the endpoint and the titer. So therefore we had this. From that information we could get the number of moles of dichromate. With the number of moles of dichromate, we do a quick little ratio, I'll put that here, of dichromate here to ethanol. So therefore we have a ratio, working out how much ethanol there is. We get the mass of ethanol using the idea of density is about 0.7. If it's not, don't kill me, but I think it's about 0.7. And we get our mils of ethanol. Okay, to get from grams into mils, we divide by density. Okay, and therefore you get our mils. We look at the dilution factor that we had. My dilution factor was a factor of 10. All right, and therefore we can get how much is in our undiluted solution. From our undiluted solution, we get our percentage, and it found out that our percentage was approximately 16.17. I should go back and look at my significant figures before I finish. 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3. So our smallest significant figures are 3 significant figures. So really, this should be 16.2% to be right with significant figures. And there you have the question answered.